My name is Jordan Frick. I'm a PhD candidate from North Carolina State University, and my research has been on mott insulating materials. Specifically, my recent work has focused on the metal halide material alpha ruthenium trichloride. We've made a few interesting discoveries. Namely, we found spreading resistance effects through STM, as well as memristic effects through IV measurements. Mott insulators are a class of material that are insulating not due to a fully filled band from traditional band theory calculations, but from high electron-electron interactions. Mott insulators are typically modeled with the Hubbard Hamiltonian. Two key components of the Hubbard Hamiltonian are the kinetic energy hopping term and the on-site potential U term. The hopping term represents the probability of an electron hopping from one site to another. The U term represents the energy gain from two electrons sitting on the same site. At high enough U with respect to T, it is energetically favorable for the electrons to remain on singularly occupied sites. This causes a splitting of the partially filled band into the fully filled lower Hubbard band and the empty upper Hubbard band, separated by a Mott gap proportional to U. One thing that's interesting about these Mott insulating materials is they can be pushed into or out of an insulating phase, what's known as a metal insulator transition. By altering the likelihood of hopping or the strength of the electron-electron interactions, you can alter the ratio of U and T. This can be done through changes in the material, like electron or hole doping. These Mott metal-to-insulator transitions have proven to be an interesting avenue for study in these highly correlated materials. It has been shown that controlling this transition can lead to numerous applications. For example, controllable metal-to-insulator transitions can be used to make memory devices like the memristor. We'll put a pin in this idea for now and return to it later in the presentation. One example of a Mott insulating material that is of particular interest for this talk is alpha ruthenium trichloride. Ruthenium trichloride is a layered material, making it easy for us to cleave off pristine surfaces for use in our scanning tunneling experiments. Through photoemission experiments, we can calculate the Mott gap, the gap between the upper and lower Hubbard band. Ruthenium chloride is approximately 2 eV. On the left, you can see an atomically resolved image of our alpha ruthenium trichloride samples obtained through scanning tunneling microscopy. In the middle, you can see average tunneling spectra at different tunneling setpoint currents, meaning the tunneling current the STM tries to maintain. What's interesting is that by raising this tunneling setpoint current, we see changes in the apparent shape of the density of states. You can see that the rise of spectral weight at negative bias, as well as the moving of spectral rate from the upper and lower Hubbard bands into the gap. This makes it seem as though the Mott gap is getting smaller. This small apparent gap is actually something that's been reported previously for ruthenium chloride by Ziadanoff et al., where they also see an extremely small gap through STS. We can increase the tunneling setpoint current even higher and show this decrease in the apparent gap size more clearly. On the top, you can see the average tunneling spectra for our alpha ruthenium chloride samples at even higher tunneling setpoint currents. On the bottom, you see the apparent gap size from a fit of the band edges of those tunneling spectra as a function of the setpoint current. It shows what appears to be a complete collapse of the Mott gap at high set points. It's worth noting that even at low set point currents, this gap is significantly lower than the 2 eV gap that we see in photoemission. This represents an interesting result. We see what looks to be the collapse of the Mott gap in STM experiments. Does this represent a metal-to-insulator transition? We think the actual mechanism behind this phenomenon is actually due to how STM experiments are performed. When doing tunneling spectroscopy, the resistance is a combination of the resistance of the tunneling barrier and the resistance of the sample itself. In highly conductive samples, you can assume that the sample resistance is much less than the tunneling resistance, so the total resistance is approximately just that tunneling resistance. However, in insulating and highly resistive samples, the sample resistance cannot be ignored. Also, by raising the tunneling setpoint current, we are decreasing the tip sample distance, as the tip needs to move closer in order to reach the required tunneling current. The lowering of the tip sample distance lowers the resistance of the tunneling barrier, making it so that the sample resistance can start to dominate the equation. This is reported previously in 6H silicon carbide, but Faux et al. Have shown similar closing of the apparent gap in their DIDV measurements. They also show that at higher tunneling setpoint currents, the IV spectroscopy shows an effective resistance decreasing, the trend becomes more linear away from the zero bias point. Shown here on the left, we have the averaged IV spectra of the ruthenium chloride samples at various tunneling setpoint currents. You see a similar trend to the silicon carbide. We see a linearization of the tunneling spectra near the Fermi energy. On the right, we have the resistance extracted from linear fits to the positive linear region of the spectra as a function of tunneling setpoint. As we increase the setpoint current, which if you recall is decreasing the tip sample distance, we're seeing a decrease in the overall resistance. This makes sense in the picture we have of the spreading resistance. We're seeing a decrease in the tunneling resistance, and we approach the expected resistance of our ruthenium chloride samples. So while this does not represent a metal to insulator transition, this result helps us address this mystery of the apparent small gap sizes seen in the ruthenium chloride STM spectroscopy. So while the metal to insulator transition does not seem to be achievable in STM experiments, we do see it in 2-pro conductivity measurements, where the metal to insulator transition can be used to show ruthenium chloride as a potential memristor material. So I mentioned this idea of a memristor earlier in the presentation, so it'd be good to define what a memristor is. Memristor was proposed as another fundamental passive circuit element by Shua et al. The signature of a memristor is what's known as a pinched hysteresis in its IV curve. A pinched hysteresis is when there's a difference in the IV characteristics when sweeping from low to high voltages versus from high to low voltages, but the curves still meet at the zero voltage, zero current point. Despite being predicted so long ago, it's only until relatively recently that we've seen reported memristor materials, namely Strukov et al.'s discovery of pinched hysteresis in TiO2 devices in their 2008 Nature publication. The reason these memristor devices are of interest is that their hysteretic IV characteristics can be used to make more complex circuit elements, like the neuristor made from memristors by Pickett et al. These neuristors mimic the neurons in the brain and contain memory of previous voltage pulses. This has been proposed as potentially bringing us closer to more scalable and neuromorphic computer architectures that have applications in machine learning. For our ruthenium chloride devices, we have taken pieces of our ruthenium chloride single crystals and painted silver epoxy contacts on the top and bottom. We can then source either a current or voltage through the sample and gain IV characteristics of these ruthenium chloride devices. A 10 kiloohm resistor is used in the voltage control measurements in order to protect the sample from sudden increases in current. Shown here is the IV curve of our ruthenium chloride device. You can see that while sweeping higher voltages, the resistance is initially fairly high, and after some threshold is reached, we see a sudden drop in the resistance until the 10 kiloohm series resistor dominates. On the backward sweep, the series resistor continues to dominate well below the threshold voltage. It's not until much lower in voltage that the resistance of the sample begins to dominate again. As the IV curve still passes through the zero voltage and zero current point, this represents a pinched hysteresis, making this a potential memristor. Furthermore, we see that this hysteresis is dependent on the rate at which we sweep. At much higher sweep rates, we see a much greater difference between these forward and backward sweeps. Another interesting result that can be seen in these ruthenium chloride devices is that when measurements are instead taken controlling the current and measuring the voltage, we see what is known as an S-shaped negative differential conductance. The threshold voltage, the maximum voltage reached, can be shown to increase as the temperature of the sample is lowered. The mechanism for this hysteretic behavior is not very well understood. The voltages used are not high enough to reach the breakdown of the 2eV Mach gap in our bulk devices. However, Oka et al. Proposed the idea of an interface-controlled metal-insulator transition. They proposed that carrier injection at the interface can create complex metal domains near the interface. In this case, the important length scale is actually the length of the band bending at the interface of the metal and insulators. Furthermore, Gibson et al. Proposed a model for how the thermal feedback can be used to model this memristic behavior. So we've proposed a combination of these two ideas. We use a Schottky diode current dependence coupled with Joule heating to model the current injection at the interface proposed by Oka, and combine it with a thermal feedback loop proposed by Gibson. This model seems to accurately reproduce the experimental data of our ruthenium chloride devices. When modeling the voltage-controlled measurements, we see the same pinched hysteresis behavior, which increases with faster simulated sweep rates. It also correctly predicts the S-shaped IV curves in the current-controlled measurements with their temperature dependence. One thing that is interesting is the high ideality factor in this model. This makes sense, however, when we remember that the picture for this mechanism is varying metal domains near the interface, so we have a series of non-ideal diode interfaces between the two contacts. So to conclude, we have shown that the low measured Mach gap in STM experiments can be explained by spreading resistance effects, and that ruthenium chloride is a potential memristor device due to its pinched hysteresis, and that we can accurately model this behavior.